The fifth question is an interesting question. So let's think about the simplest possible example where there is only a single regressor and everything have zero mean and it is scalar. So the simplest possible case without any intercept. Now, and it is nice, it is exogenous, and it satisfies the full rank assumption. But here you can think about an idea, right? So okay, we may use the OLS to identify beta, but what happens if you have an additional instrument, right? So extra instrument that satisfies relevance condition and exogeneity assumption. So even if you can use the OLS, but maybe an additional instrument can help. Okay, so let's see. And for simplicity, I'm going to assume homoscedasticity here. Okay, so the moment conditions. We are going to use the original regressor's exogeneity and we will use the extra variables exogeneity. So there are two exogeneity, and so the moment function is xz y minus beta xi. So it is 2 by 1 moment function. Okay, then let's think about its derivative. If you differentiate g with respect to beta, then it is simply minus xi times xi squared, and xi times zi, right? That is the derivative. So g0, which is defined as gi beta and beta, is minus expectation of uh, xi squared and xizi. Okay, so this is g. And let's think about omega. Omega is defined as expectation of gi, here you have to have beta 0 times gi beta 0 transpose. Okay, so then it is u squared times xz and xz. So the second guy was transposed. So that means using the homoscedasticity assumption, we have sigma squared, and then it becomes expectation of xi squared, expectation of xi and zi, expectation of xi zi, and expectation of zi squared. This is the 2 by 2 variance matrix for the moment, right? So now let's think about the optimal weight W. First, you need to think about this. K is 1, beta is one dimensional, but we have two moments, right? That's uh, uh, that means we need optimal weighting matrix for sure. Okay, and then we learned optimal weighting matrix should be the inverse of the variance matrix. Okay, so back here, like this much. But here we are going to use the trick that to ignore the sigma squared part, the homoscedasticity part will be ignored. So we are going to set actually this times sigma squared. As I said, the constant, multiplication of constant does not change the minimization problem. So it is not a problem in your weighting scheme. So our weight will be like this. That means simply the inverse of this matrix. So that means expectation of x squared times expectation of z squared minus expectation of xizi squared, and expectation of z squared minus expectation xizi minus expectation xizi and expectation x squared. So this will be the optimal weighting matrix, right? We are going to estimate this. By the way, again, I'm going to ignore this much. Okay? This is just another constant. It will be positive by the Cauchy-Schwarz inequality. So I will also ignore this much. So you may just use a weighting matrix of this form. Zi. Okay, so this is your weighting matrix. You may implement this to minimize to obtain the optimal GMM estimator. Okay, now let's think about the first order condition. The first order condition takes this form. The first order condition would look like this. It's transpose and weighting matrix times this equals to 0. This is your weighting matrix, like a first order condition, right? We are actually, it will involve some tedious algebra, but let's do that. So we know the derivative part is minus sample mean of xi squared and xizi transpose. And this part is 1 over, let me just write it down. So this is weighting matrix. And the third part here, this part looks like this. Or yi xi yizi minus beta hat n xi squared zi xizi. So this equals to 0. That is the first order condition. So from now on, let me just simplify our notation. I'm not going to write this much, okay? So like x squared means the sample mean of x squared, okay? I'm going to do the algebra. So let's multiply x squared and xz. They are, so I mean this is this got y, and it's a simplification. I am going to write this way, okay? And I will multiply here z squared minus xz and x squared times here xy and zy minus beta hat and x squared xz. This is the first order condition. Let's calculate this part first, okay? So if you multiply them, the two matrices, you are going to get multiply like this. Then x squared z squared minus xz squared. And the second row is x squared times minus xz. And plus xz times x squared. It's 0, right? That's very interesting. Still, we have xy, zy minus beta hat n x squared xz. Okay, that's 0. So it's simplified already. The second row is 0. So then if you do the algebra again, it looks like x squared z squared minus xz squared times xy minus beta hat times x squared z squared minus xz squared x squared equals 0. Okay? So anyhow, this part does not matter. It will go away, right? We know again this is not 0. So that means in the end beta hat n is xy over x squared. Remember, in our notation it was this. Okay? And you know this is OLS. Okay? So what is interesting here is, let me review what we are doing here. So we found, we are thinking about basically the classical linear regression, right? There is no difference from classical linear regression, but just I wanted to try my best to get get the best estimator. So I tried additional instrumental variable, right? I collected additional variable and I check if it may help, right? What is interesting here is, so I tried to find optimal weight. So optimal weight looked like this. And what is interesting here is every component had some weights. So I mean, what I expected here is the weight on the second moment might be 0. If the additional instrumental variable was useless, if it was not informative, then I would expect the weighting matrix will assign 0 weight on that moment. But it was not. Right? Actually, right, as you see, there were weights on both moments. That is interesting, right? So we carefully chose our weight and then we did our algebra. Then still in the end, by the structure, this part becomes 0, right? It's not because of the weight, but when you multiply the weighting matrix with the derivative, the second element becomes 0. That's the reason why the second moment was useless. Okay? So then it's OLS. So in the end, the conclusion is that additional instrumental variable is useless if x is exogenous. By the way, this is only true when homoscedasticity is assumed, right? When you assume heteroscedasticity, beta hat will not be OLS, but it will be GLS. Okay, so because the variance structure is accommodated in GLS, so anyhow, the intuition is the same thing. Okay, it's very interesting.